Hi there, and welcome back to Krishanomics. My name is Krish Vijay, and today's video is going to be different from the previous video. In the previous video, I actually had to use stock photos and I have to do a lot of editing to actually produce it. But today's video is going to be much more simpler. It's going to be just slideshows and I'll be explaining it. So I apologize for the downgrade in the quality. I find that the previous video took way too long for me to produce it, so I have to find a more efficient one, and today's one should be more efficient. So in the previous video, I talked about ARDL model. I'm just going to dive a bit more deeper into this and just show you why autoregressive models are just distributed lags in disguise. Now, in time series analysis, when we talk about distributed lag model, we assume that the independent variable, in this case, our x here, actually has a lingering effect. And so what this really means is that we will usually say that, say, x affects yt during the same period, but that, the previous x from one period before, two period before, and so forth, they still have some effect on this current yt. Now, the problem with this distributed lag model is that, especially in the case where xt and its lag, so in this case would be, say, this x, this x, this x, and so forth, they are often highly correlated. And so what happens is that your coefficient estimates can be quite unstable. Now, the second problem is what happens is that the more lags you add, you actually lose your degree of freedom. And you can think of it as this way as well. So assuming that you have, say, y, you have x, wait, let me just write it up here a bit so it become more easier. xt minus 1. And so say time period t equals to, let's say time period t starts from 0, right? You have t1, t2, t3. So let's say y is, we give some value like 10, 15, 9, and maybe 12. And let's say x is, I don't know, 100, 150, 130, 125. Now, what happened is xt minus 1 actually during time period t, there'll be nothing. But xt minus 1 would be following back previous one. So it's 100, follow this 150, and 130. So means is that when you t equals to 3, right? Say this is, let's say this is your current yt, just for example, right? So you could imagine that, its x at that particular time is, it's 1 to 5, but its xt minus 1 would be 130. It'd be one period before, right? But then what happened is that if you see this, initially we had like t from 0, 1, 2, 3, 4, right? But if we use xt minus 1, we can only use these three rows of observations. So you actually lose this observation. You can actually use that to estimate. So you can imagine that if you have more lags, then you actually lose a lot of this row of observations that you can actually use for the estimation. Now, this one simple solution for that is to just simply use the simple autoregressive model. So instead of having many x lags, you can just use one lag of the dependent variable yt1. So yep, just include this, and technically you should be able not to use a lot of xt. Like, that's the general idea here, right? From this very messy model, you get this, right? Now the logic behind this is that this yt minus 1 would act as your summary variable. So meaning to say that this yt minus 1 actually contains all these previous x values in just this one single term. Meaning to say that all this, apologize, not this. So from here, all these lag values is actually inside here. That's the general idea here. So this model is then mathematically equivalent to an infinite distributed lag model. Now the proof here is that look at this. So we start with the simple autoregressive solution. Just now the model. Sorry, not simple it's a simple autoregressive model. We start from there. So now let's say this is yt, right? Yt is equals to alpha plus delta xt, gamma yt minus 1, and then you have the error term. But if you say y is, say, one period before, so like 1, right? So very simple, you just take this t, and you just minus 1. This one, we just leave it here. You're not so interested in this. For this xt here, we also take the t and we just minus 1. This one, we just minus 2, and this one, we minus 1. That's all. Now, what we do is we take this entire thing, this yt minus 1 equals to what? We're going to plug it into equation 1. Where are we going to plug? Can you see there's a yt minus 1 here? Right, so we're going to plug it into this. And so what we will get is here. This is your yt minus 1. Can you see? And so then if you rearrange and all this, you get this. So as you can see here, your yt1, now we have xt minus 1, right? So now we have the lag of x, right, by 1 period. Now, we still have yt minus 2 here. Can you notice this? Okay, if we just continue this, say, another step, right? What we do is, we did the same thing like earlier. So we try to find what's yt minus 2. So yt minus 2 is just this, right? Remember earlier how we did this part? Right, so we're going to do the exact same thing. So yt minus 2 would just technically be this minus 2, minus 2. This will be minus 3, minus 2. That's the general idea. So this is what you will get, right? This equation 4 is what you're going to get. So then what we do is we plug back this into the remaining leg of y. So then by plugging it into that, we get this, and then we get this. So now you can see, right? We have xt minus 1, xt minus 2. Now we still have yt minus 3. So all we have to do now is just find what is yt minus 3. So probably alpha plus delta xt minus 3 plus a gamma yt minus 4 plus epsilon t minus 3. Substitute it, and we can go on and on and on. So this whole thing that we are talking about going on and on, this is actually what we call a recursive substitution. Just doing that to prove that we get what we call simple autoregressive model for an infinite distributed lag model. So yeah, so if you continue this substitution infinitely, then the yt minus n term eventually goes to 0. Now that's actually assuming that your gamma is actually, between this -1 and 1, right? Right. So just think, this part here, the geometric decay. So the coefficients for x are actually this. So this explains why the impact of a change in x fades over time. So remember we said that gamma is actually sort of like between -1 and 1, right? So it means that it's always less than 1. It's like 0.2, 0.3. So when you take something and times with something less than 1, say for example you have 5 and you multiply by, say, something that's less than 1, like 0. Say 5, right? So it's actually half of that. So it's like 2.5, right? So 5 becomes 2.5, is smaller. Now, show you where this what this means actually. This part here, this is very important. So, where we go? All right. So let's look at here. This last equation here. Okay. So as you can see, right now, what happened is that say we have x, right, and we have some delta here, right? Okay. Now, remember we said that this lambda here. Okay, we're just going to, for simplicity, we're just going to assume that this is always 0. Say 5, right? So then what happened is, let's say take xt and this is 0.5. What happened is xt values actually reduced by, oh, sorry, there's no there's no gamma here, my bad. So here is 0.5. So what happened is we are actually taking this coefficient and we multiply it by 0.5, right? So then this coefficient actually becomes smaller than this delta here. Now, here is like what you call gamma square, right? So what happened is we are taking 0.5 times 0.5 and then we times whatever this value is here, right? So this one would then become smaller than this. And then this, and then if you continue and so forth and so forth. So as you can see, right, as the lack of x increases, let's say we go to like 5 or something, it's going to become smaller and smaller. So that's technically what this sentence is talking about. Now, the efficiency part is that, so we can actually capture like the infinite lack of x with just 2 parameters, right? You can use the delta and the gamma. So remember this really lengthy equation here, this model. We can just capture it by having this very simple model, and we can only need these 2 parameters here, and we're done. So that's where the efficiency part comes in. Now, there's one thing to note here. If let's say your the thing is that now your YT actually depends on a lot of past errors, right? If you can see here, actually one of the things that we have is that the error terms here keep having a lot of lack of error terms, right? And so if your errors are actually correlated, then what's going to happen is that your y t minus 1, it's going to become correlated with your error terms, and that sort of violates the OLS assumptions, and then it can cause bias coefficients, right? So that's all for today. Probably in next video I try to talk about perhaps bounds testing approach for ARDL, and yeah, that's it for today. I hope this video has been helpful for you all, and just leave a comment if you have any questions about this. Right, see you in the next video. Bye.